In Calculus 1, you learned how to do something called a tangent line estimation, or differentials. So imagine I want to estimate the square root of 16.1, and I don't have a calculator, or I go back in time when there were no calculators. The easiest way to envision this is to think of the graph y equal f of x equals the square root function, and I want to go out to the point 16.1. So if I draw the tangent line at 16 comma f of 16, then the value on the curve would be very close to the value on the tangent line. So the idea here is if I can calculate the value on the tangent line, which should always be simple, I can use it to estimate the value on the curve. So the first thing I want to do is blow up this picture. So if I imagine that 16 is where I am, and then there's my tangent line, I would create a right triangle here. And let's say that value is 16 and that value is 16.1. On the curve, let's say this height is the y value square root of 16.1, and this is the y value on the tangent line. So I've just sort of blown this up. So the notation we give this is clearly the change in x. This right here is the change in y. On the tangent line, we call it the differential change, and we call that dx. The change in x on the curve and the change in x on the tangent line are exactly the same quantity. The change in y on the curve is the exact value we want. We're going to use the change in y on the tangent line, which is called dy. Now, this is an absolute that the independent variable, the change on the curve and the change on the tangent line, will always be the same. And for the dependent variable, we use the change on the tangent line to estimate the change on the curve. So the big picture is we are going to estimate. So that means it's asymptotic. That means it's not equal. It's impossible for it to be equal, but we expect them to be close. So the idea here, the further the line leaves the curve, the worse our estimation is, although we can always use it. If the value of the change of x is small relative to everything else, then this is a fairly simple problem. So in this picture here, our starting point, which we will call x naught, is 16. I like to call that our happy point. The actual change in x, going from 16 to 16.1, that is our delta x or dx, and that is 0.1. The rest is going to involve a calculation, which we'll do in a moment. Now, to find our equation of the tangent line, we simply use the point slope formula, which we remember is y minus the y coordinate equals slope x minus the x coordinate. Now, the one thing we do know is that x naught is going to be 16, and we know then the change here, that is exactly our dx. Right here, our change, that's exactly our dy. So the question is, what's m? Well, the slope is the derivative, because it's the slope of the tangent line at x naught. So this would be f prime of x naught. Now, this equation applies to all problems, not just this one. So in our particular problem, we said that f of x was the square root function. Therefore, f prime of x would be 1 over 2 times the square root function. Next, we know that f of 16, which is the square root of 16 or 4, we know that f prime of 16 is 1 over 2 root 16, or simply 1/8. And then finally, dx, or delta x, is 0.1. Now, the overall rule here is really simple. Whenever you're doing an estimation using a tangent line, then f of x naught plus your actual change is equal to f of x naught plus the actual change in y. The problem is we don't know this value, so we're going to estimate this with f of x naught plus dy. So in our problem here, this would become the square root of 16 plus our dy is f prime of 16, that's 1 over 8, times dx, which is 0.1, or 4 plus 1/8 times 0.1, that's exactly 4.0125. So the way we would say this finally is that the square root of 16.1 we will estimate with this. Now, that's not exactly the square root of 16.1, but if we actually got out our calculator and checked, we'd find that the square root of 16.1 is approximately 4.012. Let's see, I think we're pretty darn close in this case. 48. So we don't actually differ until well out here. So this is a pretty darn good estimation. Now we're going to continue and try a little higher level problem.
Paused.
Let's suppose we want to estimate 2.98 raised to the fourth power. So we're going to start by creating a function. Let's call it x to the fourth power. Our starting point, our happy point, will be 3. You always choose a point that's easy to work with, not one that's complicated. And our change in x, this time we went backwards, so this number will be negative 0.02. I will need f prime of x, which is 4x cubed. I will need f of 3, which is 81. I will need f prime of 3, which is 4 times 3 cubed, or 108. So we have all of the pieces of the puzzle now. So we can say that 2.98 raised to the fourth power is equal to 3 to the fourth power plus the actual change in y. We don't know the actual change in y, so we're going to use the change on the tangent line, just like before. So this would be 3 to the fourth power plus the derivative times the incremental change. That's called the differential change. So when I do this calculation on the right here, I will get exactly 78.84. So we are saying in this case that 2.98 raised to the fourth power can be estimated by 78.84. We know they're not equal because I have a 2 decimal place number raised to the fourth power, which means this is actually an 8 decimal place number. This is my estimation. So I would urge you to always check it against a calculator. They cannot be equal. They have to be very, very close. Turns out the actual value, if we calculated it, is 78.86150416. So if you notice, we don't differ till the second decimal place. Now you say, is that a good estimation or is that not a good estimation? Well, based on the fact that these numbers are almost 80 and we only differ by about 2/100ths, that's actually very, very close. Okay? We're going to continue, but now we're going to look at 3-dimensional problems. Now let's look at a 3-dimensional scenario. I'm given some function z equals f of xy, and I want to estimate this value right here, assuming that x0 and y0 are easy numbers, and that delta x and delta y are not large in comparison. So what we want to do is see how much of the previous information we can use. Well, we do know this. We do know that f of x naught plus delta x comma y naught plus delta y is equal to f of x naught y naught plus the actual change in z. What we want to do is do the estimated change in z. So delta z, which we'll estimate with something called dz, is going to be just like we did before. Before we used a tangent line, but now that we're in 3 dimensions, technically we're going to use a tangent plane. So what this will be is the derivative with respect to x evaluated at x naught y naught times the incremental change in x plus the derivative evaluated at y and then the incremental change. So this mirrors exactly what we did in the xy plane, but because we have 2 different partial derivatives, we add these results. So it turns out the actual algebra involved is almost the same. There's just this one additional step. So let's do an example. Let's consider f of xy equals 4x cubed y squared, and we want to estimate, how about f of 4.01 negative 1.02. So in this case here, we have our function, we have our happy point. Our happy point will be the point 4 comma negative 1. Our change in x, dx and delta x, which are the same, will be 0.01. Our change in y, because we're going backwards, will be negative 0.02. Okay, now from this point here, we can go directly to the answer. Well, almost. We still need the partial derivative. So fx will be 12x squared y squared. Fx evaluated at happy point will be 192. Fy, which will be 8x cubed y, Fy at happy point will be negative 512. And then finally, we'll just go ahead and calculate f of 4, negative 1. F of 4, negative 1 is exactly 256. Now I'm going to create more space so we can finish the problem. Now finishing off this problem here, we're going to get the values 256 plus 192 times 0.01 plus negative 512 times negative 0.02, and that quantity right there is exactly 268.16. Therefore, we can say then 4.01, negative 1.02, that will be estimated by this quantity here. And once again, this turns out to be absurdly close. Now, the problem is when we talk about close, close is relative. If I said I'm only off by a certain amount, you don't know if that's a lot or a little until you know how much I'm supposed to be off. So what we talk about next is what's called relative error or percent error. If I said I'm off by 1 unit, that's not very helpful. But if I said I was off by 1%, that would be a lot more helpful. 1 foot compared to a mile is a lot different than 1 foot compared to 10 feet in terms of the amount of error. So we're going to look at a very specific example here where we're going to talk about error and relative error at the same time. So I'm going to take a very simple example here. Let's consider a circular cylinder. And let's say radius and height. Let's suppose the radius is supposed to be 15 centimeters and the height is supposed to be 25 centimeters. But in the process of construction, they can both be a little bit off. In fact, let's say that the maximum error in R, that would be dr, by the way. That's exactly what that would mean. Let's say that the maximum error in R was 0.6 of a centimeter. And then the maximum error in height, which we would call dh, let's say is 0.4 of a centimeter. That's the most it can be off. It could actually be exactly. It could be 0.6 too big, it could be 0.6 too small, or anything in between. So what we want to do is calculate what is the maximum error in the volume of this shape right here if I achieve the maximum errors individually. Now we know the volume of the circular cylinder is simply pi r squared h. So using the same thing we did before, we would say the actual change in volume will be estimated by the differential change in volume. And just like before, that will involve the derivative. But now which derivative? The derivative of the volume with respect to r, that would be v sub r times the actual change, plus v sub h times the actual change. And these quantities are fairly simple to calculate. So that would be, the partial with respect to r would be 2 pi r h dr, and then here, pi r squared h dh. So now if I substitute in the given numbers, this would be 2 pi 1525.6 plus pi 15 squared 25 times 0.4. And that quantity turns out to be exactly 540 pi cubic centimeters. So the maximum error in my volume, if I am off by this much, is this. But I don't know if that's a lot or a little until I actually calculate what it's supposed to be. So now the supposed volume here, I'll go ahead and erase the stuff at the top. The volume I'm supposed to get was pi r squared h, okay, which is exactly 5,625 pi cubic centimeters. So this is our maximum error. This is what it's supposed to be. So now if we want to calculate the maximum relative error, then we'd say that delta V over V, which is estimated by dV over V, is equal to 540 pi cubic centimeters over 5,625 pi cubic centimeters. And that number is exactly 0.096 or 9.6%. So this is what we would call our maximum relative error. It's not exactly, it's an estimation, but it's a ridiculously close estimation. So this is differentials.